Let's talk about something we all use every single moment of every day, but almost never think about: electricity. We're going to trace its incredible journey, all the way from where it's made, right to the outlet in your wall.
I mean, really think about it. It's such a simple action, right? You do it without a second thought. But that little flick, it connects you to something truly massive, a system of absolutely breathtaking scale. And that's not an exaggeration. The electrical grid isn't just a bunch of wires and poles. It's a single continent-spanning machine with all its parts humming in perfect sync. So let's follow that flow of energy, and we're going to start with the basics. Our journey has to start at the atomic level, right? We have to understand the one thing that makes it all possible: the electric current itself.
You know, the easiest way to wrap your head around this is to picture water flowing through a pipe. In a wire, it's not water molecules, it's electrons. And the amount of flow, how much is rushing past a single point every second, well, that's the current. We measure it in amps. So more amps just means more electrons are flowing. Simple as that.
Now, here's a fun little quirk of history. When people like Benjamin Franklin first started studying electricity, they had to take a guess at which way the charge was flowing. They bet on it going from positive to negative, and, well, they guessed wrong. Turns out it's the negatively charged electrons that are actually doing the moving, so they flow the other way. But to this day, we still use that original conventional current in a lot of diagrams, kind of like a tribute to the pioneers, even though we know the reality is the exact opposite.
Okay, so we've got this flow of electrons, but where does it start? How do you get it going? For that, we've got to go right to the source, the power plant, where these amazing machines called generators work their magic.
And it all comes down to this guy, Michael Faraday, and a discovery he made way back in 1831. He figured out that if you move a conductor, in this case a simple copper disc, through a magnetic field, you can actually create an electric current. It's called electromagnetic induction, and it is no joke, the principle behind almost all of the electricity we generate today. It changed everything.
So modern power plants are really just enormous, sophisticated factories for putting Faraday's principle to work. And here's the key thing to realize: whether you're burning coal, splitting atoms in a nuclear reactor, or using the wind, the end goal is always the same: make something spin. That spinning turbine then turns a generator, which is just a gigantic version of Faraday's little disk, and that creates a massive electric current.
And just look at the evolution here. It's incredible. On the left, you've got one of the very first dynamos from the 1830s. On the right, a modern turbo generator that can power an entire city. The scale is it's mind-boggling. But the physics making it all work, it's exactly the same. Okay, so we've managed to generate a colossal amount of electric current. Fantastic. But now we have a whole new problem. How do you move that power over hundreds, maybe thousands of miles without losing most of it on the way?
And this is a serious challenge. Any wire has some resistance, and that resistance makes it heat up as current flows through it. If you try to push a really high current, a lot of amps, through a long wire, you lose a huge amount of that power as waste heat. It would be incredibly inefficient.
The solution is this absolutely brilliant device, the transformer. What it does is take an alternating current, or AC, and change its voltage. It can step it up to make the voltage higher, or step it down to make it lower. This single invention is the key that unlocked our modern, long-distance power grid. So here's the magic trick, the big trade-off. At the power plant, they use a step-up transformer to boost the voltage to insane levels. We're talking hundreds of thousands of volts. Now when you do that, the current gets dramatically lower. And with a super low current, electricity can zip across those long-distance power lines for miles and miles with very little energy loss. It's why we can get power from a dam in the middle of a desert to a city hundreds of miles away.
So, our electricity has crossed the country on this high-voltage superhighway. Now we're at the final leg of the journey, getting it off the highway, through your neighborhood, and right into your wall socket.
You've seen these things a million times, right? Those gray cans up on telephone poles? That's it. That's the final checkpoint. This little neighborhood transformer takes the electricity from the local lines and steps it down one last time to the safe, usable 240 or 120 volts that our home appliances are built for.
Now, it's really important to remember that the grid delivers alternating current, or AC. That's because transformers need that current to constantly change direction to work. But your laptop, your phone, your TV, pretty much all modern electronics actually run on direct current, or DC. So that little power brick you plug into the wall, its main job is to act as a translator, converting the AC from the outlet into the DC your device needs.
And not all power is delivered the same way either. Most of our homes get what's called single-phase power, which is totally fine for lights and a toaster, but big industrial motors, like in a factory, they need a smoother, more powerful supply called three-phase power, which can deliver a lot more juice, a lot more consistently.
So there you have it. That's the incredible journey electricity's been taking for the last 100 years. But that journey is now changing in some really fundamental ways.
If you just look at where our power comes from globally right now, in 2024, yeah, we still rely heavily on fossil fuels like coal and natural gas. But look at renewables like hydro and wind. They're becoming really major players in this whole energy mix.
And this change in sources is also completely changing the grid itself. You see, for a century, electricity was a one-way street. Big power plant sends power out to you.
That's it. But now, with things like rooftop solar panels and local wind projects, it's becoming a two-way network. Homes and businesses can both draw power from the grid and supply power back to it.
This picture of a wind farm is a perfect symbol for this new reality. These farms are a huge part of the new energy landscape, and they use special kinds of generators that are great for renewables because they can work efficiently even when the wind speed is all over the place.
So the one-way, centralized journey of electricity that we just followed, it literally built the modern world. But right now, a new journey is beginning, one that's more decentralized, more complex, and cleaner. And that leaves us with a huge question. How is this new path for electricity going to define our world in the next century?